No. That's okay. One, two, three, four, five, six, seven. Shall we wait till there's 10?
Okay.
10 people? At least?
Alright.
Or should we just go?
Wait 50 minutes first.
Huh?
50 minutes.
About 20?
20.
So 50%?
I reckon, like, especially like early morning, it's bad for people in time zones. Like trying to, because it's basically gonna be before us.
Yeah, it's going to be, what, 7 o'clock?
Yeah.
One more coming.
Yeah, that's the time I woke up to get here.
Shall we like wait for another 4 or 5 minutes and then start?
Yes. Let's do 4 minutes.
So do we not get the other room to use? No?
Not yet.
Oh,
That's what uni is.
Bonjour.
Hello.
Just in case.
It's Power Man.
Power. My special power would be charging laptops.
Yeah, power.
Are we waiting for students?
Yes. I just thought, or you could consider this like one of the most art house lectures ever. Just us looking at this wacky picture.
Are you going to teach Isochrone map today?
Yeah.
I thought it was next week.
Well, let's do it today.
Fine. Whatever.
Whatever.
Yeah.
What was today meant to be?
Street sections.
Yeah,
Let's
yeah.
keep going with urban planning report thing.
Yeah, that's this ties into street sections in a way. We're
Uh,
talking about streets.
Yeah. Yeah.
I was thinking of just introducing this first, and then we'll code it later.
I just made a logic that will crash Grasshopper as well.
Yeah. It won't crash it. It just
Yeah.
won't run.
Yeah.
Okay. Almost there. Can you guys can obviously hear me reasonably well. There's one that's up here, man.
Yep. Have you shown them the Magnificent? Magnificent, the modern version of this beautiful map.
No.
I'll show them later.
I want to show this because it's actually a bit shit, which is good. It's good. Okay, let's get going. We've got enough people now. So. What I've discovered, especially for like we're not necessarily going to be able to teach you guys how to be urban planners. I don't think we can teach you guys how to be architects or industrial designers or interior designers or anything. Really, we can just teach you guys how to be problem solvers because this is really an in-between class, in between a whole bunch of built environment faculties. But the key thing is that we're looking at how to logically approach things with code. And one of the most common things I've seen computational designers do in urban planning is a task called the Isochrone, which stands for equal time. Here's an example of an old sort of like 1915 map, or maybe 1920s map of Melbourne. And you can see down here in the bottom, there's a legend stating 0 to 10 minutes in this sort of lilac purple, through to 50 to 60 in yellow minutes. If we jump back to this map, this one specific map is saying if you start at this point here, it'll take an hour to get to anywhere that's in yellow through public transport. Now, and then any gradient in between, and you get these little islands here. Can you think of maybe why there would be an island? So why does it take less time to get to St Albans than it does to get sort of in between Albion and St Albans? Yeah. So there's a tram line that runs through here, and you obviously can't get off the tram halfway in between, and so you have to get off at St Albans, and then this distance that's this time that's taking is walking. And so isochrones are usually associated with public transport, hence why we end up with this map of Melbourne, or this map of France. This map of France is not for public transport. This is if you want to send a letter, or a telegram. So there's a telegram post in Paris, and let's say you want to reach somewhere in the south here. I'm not going to be able to zoom in very far, but somewhere in the south of France. Then this map was made to help people work out, well, if I do send a telegram, how long is that telegram going to take to get to where I want it to go? Because some dude on a bike or a motorbike or something has to ride to the south of France with that little piece of paper, because there was no telegraph lines to take you there. And so a map like this, what else could it be useful for? Like if you just cast your mind back to 1882 and you were working for a telegraph company, what would you use this map for other than telling people how long it would take to set up to send a telegram? Anybody? You're a company.
How much money you should spend?
You know how much money, like people are going to send telegrams here and they're going to pay a certain amount of money, right? But if you're trying to sell a product, what's important about communication? Yeah. And so if I was to build another telegraph station, where would the best place be?
Halfway in the middle.
Really? So this map is probably the best map that you would go to work out where to put it, right? Because where's the worst place in all of France? It's probably this little point here, or these points up here, and they're in the mountains. So, but the thing is, there's going to be a point somewhere in here that has the best coverage that overlaps with Paris. Yeah? And so, even though we might use isochrones to work out where is a good place to put a train station to work out catchments for train stations. It's also a tool that you could use for any kind of urban planning to work out, okay, what is the impact of my particular urban planning intervention in the urban fabric, and how does that affect people's movement, or how many people, local people, will I be encouraging to come to my building? So, for example, we mentioned last week, you're building a giant office tower or residential tower block. What effect is that tower going to have on your local urban fabric? It's got a limited floor space ratio because the council has decided that we only want a maximum number of people in the area. Our infrastructure can only handle so much. So, but there is a point in time where you might be working for a company or a government of any size that needs to decide, well, how many people can actually get to this area? What is our infrastructure? If we were to put in a higher floor space ratio, what is that going to cause? Okay. So later today we're going to work on how to code isochrones, but first what we're going to do is just focus on what is this actual thing that the isochrone is representing, and that is the street. I emailed you guys a PDF, right? I must have put that in my Dropbox. It must have been big enough. Come on, it's going to be in here somewhere. Is that our room making that noise? Here we go. So now, this usually happens in master plans. It happens in urban plans. Usually, what needs to happen is the urban planning team will work out what typology of their streets they want. And in this case, this is specifically a pedestrian street. It's 20 meters wide, so that they've made a decision on what type of light access they want into that space, and then they've defined a colonnade of trees that run down that, and they've even specified the tree. But here you go. Here's one that needs to allow for vehicular access, but they want it to have the same feeling as a pedestrian or at least park green street. And you probably noticed that a lot of the streets around UNSW are quite pedestrian friendly versus car friendly. For example, that ridiculous street that's just at the back of the Square House, which is where everyone delivers, like big trucks deliver stuff to this building, but it's actually very ill considered for trucks. It's actually almost like a pedestrian road. There's no footpath. So, where are we? So this guy's got a pedestrian footpath of 4 meters. Then there's a strip of trees that sits within that for about 1 meter, but that could change, like it's variable. Then we've got a 4 meter road, a 3 meter median strip that's planted, another 4 meter road, and then that's repeated. It's a mirrored scenario. So what we're going to code today is the a way of scripting these types of street sections. Hello. Is it Russell?
Owen.
Owen. It's the mask. And this will have a major effect on the isochrone, in a way, and we'll see that soon. So I set a challenge when we were planning this particular course with Leo that this could be done using a thing called space or shape syntax. Pardon?
Tree search algorithm or shape syntax?
It's what? Huh?
Yeah,
What was the first thing you said?
I thought it's more tree search algorithms we're going to teach them, like block first or depth first algorithm and A star, that type of algorithms to search along the tree structure, the graph.
We'll do that.
Okay.
We'll do that. We'll do that probably in the second half of today.
I have to prepare for that.
Pardon?
I have to prepare for that.
Oh, I can do that. It's fun. It's all good. So, the shape syntax is it's quite an old idea in computational design, and it's one that I think has failed a lot of people. It's this idea that you can code space using the minimal amount of coding syntax. I'll actually pull it up just so that I just want to make sure that you guys know that we're not actually using space syntax, but we're effectively defining one. Let's do shape syntax. So, back in the day when computers couldn't do too much, especially with geometry, or at least people couldn't get their heads around it. That's not even a thing. Here we go. They would try to develop these sort of syntaxes so that if someone didn't have to learn how to code, like they didn't have to learn BASIC or C or binary. Instead, people tried to create these text and number strings to help generate these types of shapes. And these strings eventually could get more complicated, as in they could add sort of recursive and various other complicated elements to it, and they could also go 3D. But it was rather limited. So if you wrote a string of ones, then you get a line. Like imagine this is just a grid of squares, and these lines are those squares are 1 unit in size. Block, 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 block. And then an N actually just denotes new line. And so if you want to draw a vertical line, it's 1N, 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 blah, 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 blah. In theory, in practice, the way that we code in Python and in Grasshopper is actually just a more advanced version of space and shape syntax. So we're just sort of saying, okay, here's a set of instructions to draw a shape or geometry, blah, 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 and the software draws it. So the thing is, people still try and do stuff with this. They try and create these syntaxes, but they usually fail. What they're actually trying to do is come up with a user-friendly, easy, standardized way of creating space, and it usually fails the instant you want to use it anywhere other than like the academic research environment that you're actually using it. and hence why we end up like you guys are learning how to code instead of no one sort of invented the amazing shape syntax method that that solves every problem. But we can at least take the idea of shape syntax to make some of our coding simpler. So in Grasshopper, we could say, okay, we've got a bunch of shape syntaxes. We want to build a street. Can you build that street using a shape syntax that says side for sidewalk, that's 4 meters, then a planting strip, that's 1 meter, then a lane, which is 4 meters, then a median, that's 3, then another lane, and then you could actually do 1.5, and then at the end say right? And that could be a shape syntax, right? The thing is, we have to define the code that runs that shape syntax, that runs it. Do you guys see what I've done here? In that I've just sort of written a string of instructions. Make a sidewalk, and then I've defined a dimension for that. Make a planting area. And we could literally write this out. Planting. Each of those instructions has an argument. Like, we could even, if I just make this a little bit more like obvious, does this remind you of any coding language that you've learnt? Anyone? What coding languages have you learned? Python. Does that remind you of Python? Huh? Kind of? Do you guys remember what functions look like in Python? We'll define one, just simply. It's just a name of a function, and effectively what arguments go into that function. So, in a way, we're just taking the idea of a text coding language, which is designed to be really complicated. It allows you to do really complicated things. We're taking the ideas of that and distilling them to just a series of functions and arguments, and those arguments could just be exactly one value, and that value is always a dimension. And then maybe a special at the end. Okay? Does that make sense? So, what we need to do is we need to work out how to tell Grasshopper how to interpret this string, and then give Grasshopper the instructions to which functions it needs to run. And what we're going to do is we're just going to work on maybe 1 or 2 of these functions. So we'll just say, okay, let's go for a sidewalk with a lane, and then you guys can start working out later how to do the rest, and we'll do that with a mirror. Is everyone cool with that? Okay. So if I was going to draw a sidewalk in Grasshopper, if I was just going to code a sidewalk, what would you do? What is the pseudocode for a sidewalk? And I'm telling you now, it's more complicated than you think. So if I were to draw one just in Rhino, can anyone, maybe someone on the internet, give me instructions as to draw a sidewalk?
2 lines.
Huh?
2 lines.
2 lines? What's the first line?
Sidewalk.
Pardon?
Like any lines.
Any lines? Like this? Is that a sidewalk?
2 parallel lines.
So I'm going to draw 2 parallel lines. I'm trying to get you guys to think in the same way the computer does. There's 2 parallel lines. When I say sidewalk,
Oh,
I mean like this.
so there's a whole thing.
Pardon?
The whole thing or only the pedestrian?
Just the sidewalk. Just that part.
Only this section or just this section?
Yeah, we're drawing a section line. A line? Okay, I'll draw a line. There's our sidewalk.
Horizontal line.
Okay, that's the key word I want to hear. Horizontal. How many of you think you've walked on a horizontal sidewalk before? You probably have, but how many of you think you've walked on a good horizontal sidewalk before? Huh? Almost no horizontal sidewalks are good.
Oh, 2 points.
Huh?
2 points. Okay, that's it.
Usually, if you want a good sidewalk, it needs to have a slope on it.
Yeah.
Always. Because what's going to happen when rain falls on this sidewalk? You're going to not just end up with puddles. If that sidewalk is flat and you're in a flat environment, you're going to end up with flooding. Basically, your people are going to be, if they're walking down that road, even in a regular rain, not a heavy one, it's going to be pooling with water. And so generally, what do we do when we care about removing water from a road? Where do we put it? We put it in the gutter, right? Is it usually called the gutter on a road? I don't know much from any road. They're called gutters, aren't they? Yeah. So generally, when we see roads, we think of them as flat, but they're actually they look more like this. And I'm going to hit you with your first note that you should take down. The standard in Australia for the maximum that you can make the cross slope of any sidewalk or walkway is 1 in 40. What that means is for every 40 meters that you travel crossways on that sidewalk, the sidewalk will lift up 1 meter. That's 1 in 40. And we're going to talk about ramps later in the course, and you're going to be hearing 1 in 14, 1 in 16, 1 in 32, 1 in 40, quite a lot there. And so what I want you to get used to is that is, in a way, a means to communicate an angle for people. So it's a little bit easier in a ramping scenario to think that. But for us, we're going to have to turn that 1 in 40 into an angle. And my suggestion is if you're ever making a sidewalk or walkway or anything like that, you should always consider that 1 in 40 angle. Don't forget it. It needs to be there in some way. Okay? So if we're building a sidewalk, we need to make sure that it's angled, and it needs to be angled towards the gutter. So if I had a string here, with Sidewalk for lane 4, we've got an issue in that I haven't communicated within this street where the gutter is. So our syntax needs to have, as well, a gutter. And I think the way that we would do that is with a special character rather than typing gutter. So shall we make gutters exclamation points? Then a lane, so that's this guy here. They will also have a camber slope to them because we don't want cars driving in floods when it's not really raining that much. And so they're going to be directing their water to their gutters as well. And in this case, we're going to mirror that. So we're really simply just drawing a cambered angled line, a curb or a gutter of some kind, then another cambered angled line, and flipping that. Yeah? So we're going to do some string manipulation using Grasshopper. Have you guys done any string manipulation with Grasshopper? String analysis, anything like that? Okay. Have any of you learned about Regex? Regex?
I don't.
You haven't?
Regex.
Okay. I love Regex. Regex is probably one of the most useful skills, other than learning like Python, actually, I'd say Python's probably the most useful thing I've ever learnt. But Regex is a close second. It should be taught in high school. If you go to a web browser and search Regex, actually if you just type Regex, it will show you Regexer. This is a nice little sandbox playground for learning Regex. It's a very useful tool. It gives you everything you need to play around with it. It will give you a default set of text. So here I've got this text that says Regex was created by gskinner.com and is proudly hosted by Media Temple. And at the top there is the Regex syntax, which is telling us, if I just look at this here, A to Z in brackets with a /w and a plus, what that particular regex function or expression is doing is it's selecting the words regexer, media temple, edit, expression, text, role, PCRE, JavaScript, regex, blah 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 blah. Can anyone notice what's similar about the words that are selected?
It includes all the words with one cap.
At least one capital. Yeah. So this particular regex string is a string to give instructions to a pattern of selection, and that pattern of selection is select words that start with a capital letter. Okay? I can write just off the top of my head with regex select numbers, and we can see this text has no numbers in it whatsoever. But if I throw in cheat sheet includes a cheat sheet 0, 1, 2, 3, we can see that that's selected there, and you can see each of those is being selected individually. There's like a little gap between. There's a little gap between each of the numbers. I can code this to make sure that it's selecting that as a full string of text as well. So that there's a cheat sheet in this particular website, which tells you, okay, a dot is any character. So if I throw a dot in there, we've got that selects everything. There's how to select just words. So if I type W and plus, and you can see they've got plus down here. That's selecting any character that then makes up a word. So that's selecting all the words, and so on and so forth. So I don't want to teach you guys regex, because regex is a complicated thing, but just know that it exists and it works in Grasshopper. It works in most coding languages. It works in InDesign. It works in Excel. It works in Word. They've all included regex into them in some way, and it's very useful. And not to repeat myself, so you know it exists, and then what I've found is it's probably the easiest just to basically either test out what you're doing in regexer or just Google what you want to do. Like, I want to select all blah 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 using regex. Someone on Stack Exchange somewhere will be like, oh, here you go. It's so simple. It's just this blah 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 blah, and you'll get to learn it. It's everywhere. Now that you know it exists, you'll see it. So what we want to do is we want to use regex to work out. Actually, can we actually even use regex? We can't use it in Grasshopper for this. Okay, never mind. Either way, you now know that regex exists, but that's not going to solve this particular problem. What we're going to do instead, basically what we need is to split this text up. The Grasshopper method of splitting the text. Sorry, I forgot, but effectively, for us to split this, we're going to need to work out where there's numbers, and the problem is unless we open Python up in Grasshopper, there's no way of using a split or replace or whatever that uses a regex function. The only thing that Grasshopper does with regex is this match text, which you can throw that text in and tell it, okay, tell me if the number 4 is in this, and it will then give you a true or false. Sorry, my head was just in Python for a moment there. So what we're probably going to do for this is we're going to have to include in our syntax a delimiter, and we'll make that delimiter comma. So we've got a comma in between Sidewalk and our exclamation point, and we've got a comma between that and lane 4. And then, just to make this as simple as possible, hey dude, we're also going to put another delimiter in between our numbers and our words. So, just so you know, if you were going to make a syntax for this, like a professional one that you want to use multiple times, then you probably would run it maybe through a Python, you call it deserializer, that would do those regex searches and would sort of mean that you don't need to add those delimiters. But in this case, just to be quick, we won't do that. So we've got our string. What we want to do is break that up. So we're going to use the text split. All the special functions that we've decided that we want to happen over this are at the end using this pipe character. So what we will do first is split our string up, which will give us our functions with their values and the specials. So we're going to split that list up, and I'm just going to use, actually, let's grab that. Cool. I'm going to use list item, and we're going to focus on the numbers for now. and then we're going to just use the same function. So we're going to text split. We're going to split by commas, which will give us our individual instructions for our sidewalk. And then we're going to text split yet again. And that's going to give us the name of the function, and then it's an individual argument that defines what's happening with it. And this is where things are going to get really complicated. Go for it, man. So, what we're about to do is we're about to bully Grasshopper into working a different way to what it normally does. So, in a declarative programming language like Python or JavaScript or C# or whatever, what you primarily do is you define functions that are initialized prior to doing any instructions, and then you then write instructive code that calls on those functions, those declarative functions. So in Python we could say, hey, iterate over this, and in that iteration first do a sidewalk, then do a gutter, then do a lane. But the thing is, Grasshopper doesn't work that way. Grasshopper only works in a linear left to right fashion. And so, unfortunately, we have to bully Grasshopper into thinking declaratively for this to work. And there's a few ways of doing it. The simplest way is to use a plugin called Anemone. So what Anemone does is it makes Grasshopper function iteratively, like as if you were to iterate over a loop or iterate whilst something is true. There are multiple different plugins that allow that to happen. My favorite is Anemone. Does everyone here, have you heard of Anemone yet?
Yeah.
You've heard of it?
You have to use it a little bit, right?
Yeah? Okay, so you've used Anemone?
Yeah, but very briefly.
So that means it's installed on your computers?
Yeah, please.
Good. Cool. So Anemone is basically just for a for loop for Grasshopper. So, if I make this thing Python, actually it's not it has the limitation of, if you were to look at a Python script, we're going to set r equals range, no. List length equals range 5 for I in list length. This is all Anemone is. Okay, it needs a defined number of times that it will run. And then it will just iterate over a list that many times. And so the list that you run over doesn't necessarily, it won't run over a list, it will run a function for the number of times that you've defined. And so it won't do whiles, you kind of have to force it to think as if it is doing a while function. So that means it can't run for infinity, basically. So the basic functions of Anemone are the loop start and loop end, which we can almost think of as like the beginning of a for loop and the return tab indentation at the end of a Python code, and we tell Anemone that what is the start and end function of it through this little arrow connection. So we're going to use Anemone, but before we do that, we're just going to write part of the code. Okay? So the first part of this code is make a sidewalk and make it 4 meters long. Okay? So if we just say here we're going to run the sidewalk code, write the sidewalk code. And sidewalk is actually going to be a very similar code maybe to the laneway, the car lane. But we'll soon see what that means.
Okay.
Yeah.
Do you remember which folder the GHA plugin items go to? Is it?
If you go to file, have you got Grasshopper open?
Yeah.
If you go file, special folders, it'll be under the
Is it user or component?
GHA.
I think it's component.
GHA, I believe, is components. So if you click on components, that's going to show you all the GHA. That's,
Okay, I just have to do that little unblock thing.
yeah. So you right click it, properties, and then there's unblock there. I don't even like. Yeah, it's just people trying to be very secure. Windows being very secure. So we're working on the sidewalk code, and to start off with, we need a point. So we're going to build our sidewalk off the 0 point. And we might move it later to make things easier. We're then going to draw a line off that, and that line we're going to draw off is going to be in the x direction. And then the length we're going to use is going to be 4. And this script is going to seem really simple in a moment. Very simple. Okay, so we want to have this thing, we need this thing to have a slope, right? So if I was drawing a sidewalk and it was, let's say the gutter was here, we need our slope to know where it is in relation to a gutter. Yeah? And the likelihood of there being more than one gutter is low, as in a mirror, and the likelihood of there being more than 2 gutters on a regular road is also low. But I can tell you now, there are places in the world where there could be more than 2 gutters in a street section. There could be roads that are so large that they need it, or they could be in a location that rains so much that they might need more than a few gutters throughout the space. Yeah.
Where do they normally put the extra gutters?
What they'll do is they'll put they'll have a median strip that has another gutter.
So they put in the middle the different direction of the lanes.
Yeah. Yeah, that if they need it. So what they'll either do is they'll make this gutter absolutely massive. So I don't know if anyone's been to Singapore or somewhere in Indonesia, but there are some parts of Indonesia, if the road is large enough, the lanes are large enough, the gutters are humongous because it rains there. It rains a lot, and when it does rain, the amount of rain is humongous. You could have more than one gutter, and the only reason I'm saying this is that we need to consider that maybe when we're writing our code, we have to think: is there the possibility of there being more than one? How do we work out what's happening there? So what we would do is we need to work out, okay, if we're writing a sidewalk, where are we? Where is this sidewalk in the shape syntax? So if I just pick out these texts, and let's flatten them, just to simplify this a bit. The sidewalk is the first item, and the nearest item to it that is a gutter is item 1, right? So we can very quickly just see, okay, well, if we're drawing a sidewalk here, that sidewalk is to the left of the gutter, so the sidewalk needs to angle downwards from left to right. But we need to get Grasshopper to understand that. So when we're writing this code, we want to know, okay, sidewalk. What index is sidewalk? And I showed you guys this last week. If we use member index, that'll tell us that's index 0, right? But if I was writing a shape syntax, could I run into a problem with this code? Anyone? Could there be an issue with this?
My 1-1 sidewalk.
Exactly. So, for some reason, we've got a sidewalk in the middle of our street, but now we're being told, okay, this is 0 and 3. There's a problem there. So, fortunately, Anemone will actually tell us what index we're running on in a loop. So if I run through a loop 10 times, and I'm just going to pass the number 10 through it 10 times, if we run that loop again, as it loops through, it tells us what iteration we're on. We're on iteration 0, we're on iteration 1, 2, 3, etc. So rather than using a member index, what we're going to do is we're going to rely on Anemone C index. And for now, we're going to say that's index 0. I'll just get rid of that other sidewalk. So that's going to be index 0. Eventually, when we plug this into Anemone, this guy is going to be fed in with that C value instead of using this. Okay? So we've got index 0 here, but we do want to use this member index to analyze where we have exclamation points. So we've got an exclamation point at 1, and if we had more, so for some reason we've got some weird road, there's 1 and 3. So, this is going to be a weird one. How do you work out which one is closest? There's a few ways of doing it, but which of these is closest? to 0. 1, right? I want you guys to don't like. I'm gonna throw you guys soft questions. They might seem easy because they are easy, and then some of them will be very hard.
Yeah. Sometimes the operations get a bit too quick, so I'm like focusing
Okay.
on like catching up.
All good. Okay, so we want to work out which gutter is closest. The reason is we don't. If there was a gutter over here for some reason in our section, we want this one to be relating to this gutter, the closest to it, basically. Hey, I'm guessing you're Russell. No, there's no problem. And what we're going to do is we're just going to ignore distance at the moment. We really care about whether it's adjacent in the syntax rather than close to it with a distance. So we can either do a sort function. So we would say, like if this was a gutter over here, it would be 4. So it's x minus y, and we want to make sure that value is absolute. So the numbers 1, 2, and 3 minus 0, absolute. That's going to give us 1 and 3, because that number hasn't changed. Let me just make this. I just want to make sure that you guys see this in a way that, because the number 0 is going to just confuse everyone. So what I'm going to do is I'm just going to make our sidewalk act as if it's number 1, not number 0. And the gutter and the other gutter is at 2 and 4. So if I subtract 1 from 2 and 4, I get 1 and 3. And then if I sort 1 and 3, which it won't sort any differently, let's just put our sidewalk on the opposite side of the second gutter. So our sidewalk is now at 4. We've got the first gutter, which is 1 at index 1, and the second gutter, which is at index 3, is a distance of. So the first one's 3 away from that sidewalk now, and the second one is 1 away, right? So I've put the sidewalk here now. It's at the end. There's a gutter here that's 1, 2, 3 away, and then there's another gutter which is 1 away. Does that make sense? Cool. We care about this gutter, index 3's gutter. So if we sort our numbers so that they say 1 and 3, we can sort synchronously. Is everyone familiar with synchronous sorting? No? So if I were to ask everyone in the room right now to stand up and get in a line from youngest to oldest, right? What you're doing is you all have to say, well, I'm this old. I was born at this date. I'm this many days old, right? So someone might be, 5,000 days old, and someone might be 5,500 days old. And so you guys are processing the sorting of the numbers, but at the same time you've got that number associated with the person. And so you sort the people based on the number. Even though you can't sort people, like you guys are way more complex than numbers, right? You're not just one number. But what we're doing is we're sorting the number and sorting the people synchronously. And that can happen using these sorts in Grasshopper. We can sort a series, like a collection of numbers, and as long as you've got the same length of list of any other thing, and it doesn't have to be numbers, it can be curves, it can be points, it can be whatever. You can sort those things synchronously. So we've sorted this 3 and 1, which is a distance, and synchronously we get the indexes sorted 3 and 1. So the result will be 1 and 3, 3 and 1. Index 3 is 1 away, and index 1 is 3 away. Right? And so if we pick out the first item of that list, which is 3, that's the index of the gutter closest to the item that we're just working on, this sidewalk. Cool? Now, the next thing is we need to work out, is that number